I think we will go ahead and get started. So good morning, everyone, and welcome to the first Trainee Talks of the fall semester. I'd like to begin by giving a very warm welcome to our 11 new trainees who have joined our CREATE group this September. For those of you who are with us for the first time, Trainee Talks is a monthly webinar series showcasing the research topics of CREATE SE4AI graduate students in their area of expertise related to software engineering and AI. And for those of you who I haven't had the chance to meet yet, my name is Lori Akiyama, and I'm the program coordinator for CREATE SE4AI at Concordia University, and I'll be moderating the webinar today. Today, we are pleased to have two of our program trainees, Divya and Mohayemin, joining us to deliver their talks. Divya Kamath recently completed her master's degree from Queen's University under the supervision of Dr. Bram Adams and Dr. Ahmad Hassan at the MCIS and SAIL labs. Divya is now embarking on her next academic journey as a PhD student at the Software Technology Lab at McGill University, where she will be studying human-computer interaction with the goal of developing inclusive software for the neurodivergent spectrum. Divya is going to be sharing her research with us today on pragmatic approaches to schedule-less builds in continuous integration. Immediately following Divya's talks, we will hear from Mohayeminul Islam, who is working under the supervision of Dr. Sarah Nadi at the University of Alberta as a fourth-year PhD student. Mohayemin's research objective is to help developers with library migration, that is, replacing one library with another in an application. And today he's going to be sharing with us his research on characterizing Python library migrations. Wow, that's a mouthful. So usually the format that we do here in our trainee talks is we give each speaker 20 minutes to present their talk, and then we have a 10-minute Q&A session after each speaker. So we just ask that you please keep yourselves on mute until the Q&A session at the end of each speaker, and then you can ask your questions after that through the chat or by raising your hand. This webinar will be recorded as usual, and we will share the link on our CREATE website at se4ai.org and also on our YouTube channel. So with that, I'd like to turn things over to Divya. Divya, please take it away.
Thank you, Lori. I'm just going to start sharing my screen and let me know when it's visible. Is it good? Okay. Good morning, everyone. I'm sharing my thesis that I did during my master's. It's on pragmatic approaches to schedule-less built-in CI. I'm going to jump right into it with an example. So assume this is a software product, a web browser, which you want to look at the CI for. So any modern web browser is supported on many different platforms, like active versions of operating systems like Windows, Linux, and iOS, or devices like phones, desktops, and tablets. This is a web browser developer who wants to add a new feature to the web browser. So if she wants to add a new feature, she's going to push a commit to add this feature. And any commit she has to push needs to undergo testing on all supported platforms. Then this commit is merged into the code base only if the testing is successful. This is a CI pipeline generally, and it can take several hours from commit push to commit merge. And most of this is because of the testing, because testing has to be performed on all of these platforms. So it takes a really long time. In reality, on average, 40,000 code changes are submitted to Google every day. And Google has reported their CI costs in millions of dollars annually. So companies do not have enough resources to execute all builds all the time. Also, this cost of CI also eludes small companies from using CI in their code base. Let's go over some basic terminology I'm going to be using. The first one is build, which is a process of compilation and testing of code. Build pass is when compilation is successful. Same way build fail is when compilation is not successful. Builds required is a term I'm using very frequently in this presentation, which is a percentage of builds required as opposed to building all commits. So if there are 100 commits coming in by a developer and we selectively choose to build and test only 50% of them, 50 of them, so we're requiring 50% of builds, and at the same time, we're saving 50% of builds. So like I mentioned before, builds are the large reason why CI is so expensive. So many different approaches were introduced to reduce the builds in CI. The first one we're discussing, which is existing, is build outcome prediction. So assume that you have a few incoming commits pushed in by a developer. Some of these commits are going to have some bugs and some of them are not. So some of them will compile successfully and some of them are not. If you want to reduce the builds in CI, you're going to want to just merge the commits as they come in without any testing or compilation. But when you do that, if you merge a successful commit without any compilation, that's fine. But if you want to merge a failing commit without compilation, that's a problem. So you have to compile at least a few commits. And your best bet to reduce builds is to compile only the failing commits. This is the whole idea behind Smart Build Skip, which is a build outcome prediction model that is used for skipping commits. So a Smart Build Skip uses an ML model to predict the build outcome of an incoming commit. If the commit is predicted to be successful, then it is merged straight into the code base. If it is not, then they build the commit to see what the error is and do not merge it straight into the code base. Once they see a build fail, they continue building until they see a build success. This is all great, but there are a few drawbacks with Smart Build Skip. The first one is the high cost of training a model, because it's not just training, you have to maintain it, you have to retrain it, it's very expensive. And the second one is the plausible delay in failing build identification. So assume that there are a few incoming commits, and these are the predictions of the Smart Build Skip model. When the first commit comes in, Smart Build Skip predicts that it's going to be successful and skips the commit from being tested and merges it straight into the code base. When the second commit comes in, Smart Build Skip again assumes that it's going to be successful and merges it straight into the code base. But if it had compiled this commit, it would know that it's going to fail. But since it doesn't know that and it didn't do a compilation, it's going to go ahead with the prediction phase. So it's going to continue predicting incoming commits to be successful because it thinks so, and it continues to skip the commits from being compiled. It merges them straight into the code base until we come across a commit that Smart Build Skip thinks is going to fail. When Smart Build Skip thinks a commit is going to fail, it's going to build that commit to see what the error is. When it builds this commit, it's only when it's able to see the first commit that has failed. So this has caused a 6 commit delay in identifying the first failing commit. Once the Smart Build Skip has identified a failing build, it continues building until it sees a successful build. Here it has seen a successful build, so it goes back to the prediction phase and continues skipping commits that it thinks is going to be successful. The main thing to note here is the 6 commit delay, which is the main drawback of Smart Build Skip algorithm. We computed this delay in Smart Build Skip for 20 projects. We calculated this to be between 9 to 797 commits. So if you were a developer with Smart Build Skip in JRuby and you pushed in a commit, then it would take around 9 commits for you to know if your commit failed. And on the extreme left, if you see Graylog to server, it would take around 800 commits for you to know if your commit failed. And this is really bad because you don't know if 9 commits is going to take a few hours, days, weeks, or months. With that, we're going to the next existing approach, that is the batching approach. Assume again that we have a few incoming commits. The whole principle behind commit batching is to batch together a group of commits. So here we have batched 8 commits together and we compile them at once. So instead of building each individual commit and making 8 builds, we do a single build, saving 7 builds, which is really great. But not all commits are successful. Here in batching, if a single commit is failing, then the entire batch is going to fail. So developers have come up with approaches to identify failing commits in a batch. In one of the approaches, they split the batch right down the middle into 2 sub-batches. If there are any failing commits in any of the sub-batches, they're split again and again until they identify all the failing commits individually. This whole process has taken them 13 builds. Whereas if you had just compiled each commit individually, it would have just taken you 8 builds. This is the batch bisect approach, and there are many other approaches like it. If all commits were successful, batching would have been great. But there are a few drawbacks with batching too. First one is that developers need to wait for a long time for the batch build to be carried out. And the second one is that batching is not suitable for projects with higher failure rates of more than 25%. The longer wait times for developers is best explained with an example. Assume again with a batch size of 8 commits. A developer pushes in the first commit of the batch, then they have to wait for 7 more commits to fill the batch. The next commit is pushed in by another developer. They have to wait for 6 more commits to fill the batch. And this goes on. So the delay goes from 7 to 0 builds. And we have seen the median delay of such wait times to be between 1 to 6 commits. But as batch size increases, median delay also increases. The next approach is a dynamic batching approach, which is based on the principle that batch sizes do not have to be constant. First, a finite number of commits are grouped into a batch and compiled at once. If there are any failures in the batch, they are identified using any of the batching algorithms. After this, the new batch size is looked up into a lookup table by looking into it using the previous failure rate, the weighted failure rate, and the previous batch outcome. Once a lookup table gives a new batch size, that new batch size is used to compile further commits. And this new lookup table is generated using an offline simulator, which simulates the best batch sizes according to weighted failure rates. This continues for the entire project by looking up a new batch size at the end of every compilation. In dynamic batching, it requires complex calculations to calculate the weighted failure rate, especially to remember the batch size, batch outcome, and build outcomes from the beginning of the project. And also, dynamic batching lacks a lot of customizability since the simulation is going to decide your next step. In our work, we contribute by improving build outcome prediction by designing MLCI and timeout rule, which combines the smart build skip algorithm with batching algorithms. And the second, we make dynamic batching more lightweight by replacing complex mathematical models with simple heuristics. We use 2 datasets in our evaluation. The first dataset consists of 20 projects and over 79,000 commits. We use it to evaluate MLCI and the timeout rule, and we measure the performance by calculating the percentage of builds required and the median delay induced by each heuristic. And the second data set consists of 50 projects and over 200,000 commits, and we use it to evaluate lightweight dynamic batching algorithm, and we measure the performance by calculating the percentage of builds saved by each heuristic. From existing heuristics, we know that smart build skip can induce large delays in identifying failing builds. You may remember that it was between 7 to 797 commits. And we propose that builds should be scheduled more frequently to ensure that build failures are identified as early as possible. We introduced the timeout value to keep track of the number of commits elapsed since the last build was scheduled. And the timeout value is incorporated by a timeout rule and MLCI to necessitate frequent builds. In this presentation, I'm only going to present the timeout rule and the lightweight dynamic batching. Starting with the timeout rule, it combines build outcome prediction in the form of smart build skip along with static batching algorithms. We also use a timeout value, which imposes a check on the number of builds that can be consecutively skipped. Timeout rule works by predicting the build outcome of an incoming commit using smart build skip. If the commit is successful and the timeout threshold is not reached, only then the build is skipped. But if the timeout threshold is reached and the build is predicted to fail, then the batch of commit is built. And we continue building incoming commits in batches until a successful build is encountered. Seeing that with an animation, Here, there are a few incoming commits, and these are the predictions of the smart build skip algorithm. When the first, we are going to assume a timeout value of 3 and a batch size of 4. When the first commit comes in, smart build skip is going to think that this build is going to be successful, and it predicts the same. So we skip this build from any compilation and testing. Then in the second commit, smart build skip again predicts that this commit is going to be successful. So no build is scheduled, but this commit would have actually failed. In the third commit, smart build skip again assumes that this commit is going to be successful and skips the build. But at the same time, we've been incrementing a value to count the number of commits that have been consecutively skipped. At this case, we have reached a timeout threshold of 3. So in the next commit, we ignore the predictions of smart build skip and build a batch of commits. Once we have verified that this batch of commits are successful, we go back to the prediction phase. And we start incrementing the timeout value again. Then if we see a failing commit, we again build a batch of commits. The advantages is that timeout rule can lower the wait time and reduce the risk for delays, but the drawbacks is that it costs a lot to train and maintain this model. We've seen that the timeout rule achieves either similar or 0.5 commits higher median delay than commit batching techniques. Timeout rule requires between 1 to 4 commits delay, which is much less compared to the 9 to 797 commits delay of smart build skip. We also see that timeout rule reduces the builds required in comparison to batching algorithms by 36%, but it requires a median delay of 16% more builds than smart build skip. This is the cost of reducing the delays by increasing the number of builds in timeout rule. The second approach that we are discussing is the lightweight dynamic batching, which we introduced by combining batch updating techniques along with fallback algorithms like batch bisect, batch stop 4, and batch divide 4. Instead of using complex mathematical models, we use simple heuristics to update batch sizes dynamically. The heuristics are linear, exponential, random, mixed, and most frequently used. The basic principle here is that we increase a batch size if the previous batch compiled successfully, and if there are some failures in the previous batch, then we decrease the batch size. So assume that there is a factor of 2, according to which we increase and decrease the batch size. And if we're working with an exponential batch updating technique, if we have to increase the batch size because the previous batch was successfully compiled, we multiply the previous batch size with 2 to get the new batch size. And in the same way, if the previous batch was failing, we divide by 2. Seeing this as an example, let's see an initial batch of 4 commits. Since this batch is failing, we divide the batch size by 2 and get a batch of 2 commits. Since this is failing too, we divide by 2 to get a batch of 1 commit. Since this is failing, we stay at the minimum of 1 and compile a batch individually. But once we've seen a successful batch, we multiply by 2 and get a batch of 2 commits, and we multiply again by 2 and get a batch of 4 commits. This continues happening, and we only look at the outcome of the previous batch to update the batch sizes. We saw the lightweight dynamic batching perform on 50 projects on the second dataset. LWD, or lightweight dynamic batching, can save between 26 and 49% of builds. And we've seen it work best with mixed linear and exponential techniques with the batch bisect and batch stop 4 algorithm. And we've also seen it work best with the exponential dynamic batching. In comparison to existing batch updating techniques, we saw that the lightweight dynamic batching can perform equally well as the complex dynamic batching algorithms, which has the big mathematical models. And we have seen it to save more than 7% builds compared to static batching algorithms, where they're using a single batch size across the entire project. Finally, with our random batch updating technique, where we are using random batch sizes to increase or decrease the batch according to the previous batch size, we've seen this also to perform equally well as complex batching algorithms. So we're saying that you don't need complex mathematical models, and even random techniques can work equally well. Coming to our key findings, we say that both commit skipping and commit batching algorithms have their advantages and disadvantages. Build prediction algorithms induce large median delays in CI that need to be controlled with history-based timeout thresholds. Simpler build batching algorithms work equally well as complex batching techniques. In conclusion, we saw the problem of CI builds and the expensive costs of CI. We saw existing techniques to reduce the builds in CI. We saw the timeout rule and the lightweight dynamic batching. Thank you for your time. I'm open for your questions now.
Thank you so much, Divya, for your presentation. I can tell that you put a lot of thought into that, very detailed and great explanation. So now we'll just open up the floor to any questions. If anyone has a question, please go ahead for Divya.
Yes, Professor.
Okay, so thanks, Divya. Maybe I have a question about the implementation part of this, right? So you may know we've worked on CI skip stuff before. And what we found is that I think you had a point that you went through very quickly, which is simpler is better. And it's because it actually becomes very, very difficult when you have, the more advanced your techniques are, it becomes much more difficult to actually implement this in a real system. Sometimes even just the delay of like bisecting something can become prohibitively expensive to implement it. So I wanted to ask you, is there any aspect in your evaluation related to that, to the implementation detail, or how likely some technique is to be implemented?
As in the existing CI code base, like at the
pipeline? In any existing development process.
Not really. We just calculated it according to a simulator. We just because we're aware that they already use techniques like this at the background, like batching techniques are already used by some companies. So we don't know if there are any problems integrating it at the back end, but we have not evaluated it from that point of view.
Okay. All right. Thank you.
Thank you, Professor.
Okay, we have a couple more questions. Sarah, you can go ahead, and then Mohayemin.
Okay. Hi, Divya. So very nice talk. Thank you. So I had a question. Maybe I missed it. Like the techniques you're compare against, these are research techniques, right? Like they're proposed and paid. So I'm just wondering, like, do companies actually adopt any of those techniques? So like we know that it's a problem because of all these builds. We know the failed builds. We know the cost of the building. But like, have you seen in practice, whether in open source repositories or maybe companies you're aware of, that they're actually implementing some of these techniques?
According to literature, that there are companies like Google and Mozilla that batch their builds together, but so far I have not seen companies in literature where companies have used prediction models. But there are a lot of prediction models that have been proposed recently. So batching.
Yeah. I'm wondering how, if they adopt it, but yeah, like I understand they're in the literature, but thank you. I was just wondering if you have any. Thank you.
I just want to follow up on Sarah's question. So the bisect, which is Peter Rigby's work, I sat on the committee of his students. I think the work was then in collaboration with Ericsson, and they were actually using it in a collaborative way. But I guess other than Ericsson, probably not so clear how many other companies are using it.
Okay, that's good to know. Thank you.
Okay, Mohayemin, please go ahead, and then we'll have Muhammad Yusuf.
So I see in your first model in slide 12, you have you skips like some of the commits, so which may be failing. So I was wondering, how does it affect the development process? So they're just don't know that some of the commits would be failing. So this might be also related to like Imad's work, who also skipping the build. So is there any study on that?
Not yet. Actually, this is also a drawback with smart build skip algorithm, where they have skipped techniques, skipped some commits that would fail, and they wouldn't know that because they've skipped it. But they don't talk about how they would go back into identifying what was failing. So that is a drawback with smart build skip, but here we are mainly reducing the time in which they will identify that something failed. For example, in this slide, the third commit was also failing, then and the fourth commit was also failing. Then by the time they compile this, they would know much more recently that something's failed. And there are techniques that they can go back, but it's not discussed in literature yet. I hope that answers.
Yeah, thank you.
Thank you. Yusuf?
Yes. Hello, are you able to hear me?
Yeah, I can.
Yes. First of all, thank you for the great presentation. I was just wondering if you could go to the empirical evaluation slide.
Are you talking about the data sets? Okay.
Yes, the data sets here. I think one question I had was, I think later on in the presentation, you also described like some heuristics which you have employed, like especially the part of like gradually dividing by 2. One question I had was like, how were you able to reach these heuristics? I was just curious.
How we were able to reach the heuristics of dividing and multiplying by 2, the lightweight
Yes.
dynamic batching?
Yeah.
The answer is, so there are existing batching techniques that require complex calculations, and these actually came up because static batching has a drawback. For example, there are projects which have a lot of failing builds, and if you use a static batch size of suppose 4 or 8 commits, and you continue building commits in batches of 8, and there are build failures, because build failures first of all occur together. That is one of the assumed concepts of CI. And when this happens, we still have to, because of static batching, we still have to batch together in groups of 8. And this is going to cost us extra builds, like I showed in the previous slide of static batching. But if you can change the batch size, and if you know that there's a failure coming in and you can reduce the batch size, you can reduce it to 1 build and not require more builds for identifying failing builds in a batch. So this is how dynamic batching came into the picture, and that's how we came up with the simple lightweight batching techniques.
Oh, okay, perfect. Thank you. But I was just curious, like, how did you guys actually reach like the specific heuristic of dividing by 2? I suppose you must have implemented some kind of trial and error approach to reach that number, or?
We've tried it with 2, 3, 4, and so on. So we just reported with that was an example, but we have reported our results with different values of factor. Divide by 2, divide by 3, divide by 4, so on.
Okay, perfect. Thank you very much.
Okay, if there are no further questions for Divya, I'd like to thank her very much for her presentation. And in the interest of time, I think we should move on to Mohayemin. So
thank you so much.
Thank you, Divya. Good luck to you with your PhD.
Thank you.
And Mohayemin, please go ahead and share your screen whenever you're ready.
Yeah, you can see my screen, right?
Yes, looks great.
Okay. Hello, everyone. I am Mohayeminul Islam. I'm a PhD student from the University of Alberta. I'm doing PhD under supervision of Dr. Saranadi. Today, I'll discuss how we built a taxonomy of library migrations to characterize them. So let's see what we mean by a library migration. So let's say these developers of CQHTTP, like a open source project, they started developing their app with a library named Bottle, which is a lightweight and fast web application framework. But as their software started to grow, this library Bottle couldn't anymore like support the needs they were looking for. So the developers start looking for an alternative and find another framework, Flask, which is much more feature rich and probably would suffice for their need. So they switch from Bottle to Flask. So this process of switching from one library to another in an application is called a library migration. So like library migration can happen for like many reasons. For example, like sometimes the library that is being used may be out of date, or then may need additional features, or like sometimes there might be licensing issues as well. So as you can see that when you are doing a migration, then you need to change the code. So this changing of the code for the sake of migration, we call them migration-related code changes. So in this example, we have two specific cases of migration-related code changes. So this Bottle function is replaced with Flask, and this post is replaced with route. So then we have this term analogous library pair. In this example, Bottle and Flask. So these are the library pairs which provide similar functionality, and and migration is possible between them. And then we have these tasks of like when we do a migration. So the first is API mapping, where we identify that this Bottle function should be replaced with Flask and this post should be replaced with route. Then there is actually changing this code to use Flask instead of Bottle. So for example, in the first one, there was a need to add an additional parameter. So it's the same for the second one. So there might be other type of changes that might be required. So based on this and like previous studies, we find that manually doing the migration can be very tedious depending on how often you use the original library. And it can also take a lot of time, and there might be like errors that you don't want to be in your system just for the migration. So now that means that automating this library migration process might be helpful. So as a researcher, you may be asking like to be able to support migrations automation, you may like want to know like what are the common types of code changes. So you just look up in the like literature, and it will say it's not sure because there is like no like systematic classification of the code changes. So looking a little bit more in the existing techniques, we find some other things, that most of the studies are on Java, and also there is a limited support for client code transformation for library migration. There are some for like migrating between versions of the same library, but we know of just one which support migration between different libraries, which is also have like very limited support. So based on this, we design our study. So we first build a taxonomy of migration-related code changes. We call it PyMigTax. Then we do an empirical study of the migrations, and we do this for Python because of its growing popularity. So let's see how we built the taxonomy. So we first prepared some data, and then we prepared a draft taxonomy, and then we finalized our taxonomy. So we'll look into a more bit detail about these steps. So for the data preparation, we found two existing migration data sets. The first one is self-admitted library migration, so which has about 5,000 migrations. So that means 5,000 commits that is marked as, okay, in this commit, there is a migration from this library to this other library, but they don't mark the code change locations. And then there is PyMigBench, which we developed earlier, which has much fewer migrations, but it includes the code change locations. Just to give a little bit of a more idea what is in these two data sets. For example, for the SLM, it will just say that in this commit, there is a migration from bottle to flask. But PyMigBench would say that these two sets of lines have code changes happening in there. We'll see that this information is very useful for the next steps. So from these two data sets, we've from the first one, SLM, we choose 262 migrations randomly, and from the PyMigBench, we take all the migrations and we build another data set. We call it PyMigBench version 2. So it has 337 migrations and about 1,900 code changes. Okay, so the first step, the next step is building a draft taxonomy. So we basically are not sure what is out there in the migrations, right? So what we do is that we use the PyMigBench dataset for this this step, because it has the code change locations marked. So what we do is that we individually analyze some code changes, and then we discuss in the team. So when we are doing that, we just try to find what interesting is happening in those migrations. For example, in this one, we find that a function is replaced by another function where the function's name is different. This is probably a very trivial example, but something more may be happening. For example, we find that sometimes multiple functions may be replacing multiple functions, where we cannot say, okay, this is one function that is replacing the other one, but as a whole, a set of functions can be replacing as a set of functions. And then there are other types of program elements involved. Sometimes attributes, decorators, they also play a role in migrations. So basically, from our very draft analysis, we find that there are three important things that might be worth looking at in the code changes. So one is which program elements are being affected, for example, functions or attributes, things like that. And then we need to look at how many of them are being replaced by how many. For example, 2 replacing 3. So we kind of shorten it as if more than one, then we call it many. Then there are additional properties. For example, in the third one, there is a typecast. So based on this, we prepared this draft taxonomy, where the first column we had identified these 4 types of program elements, and then a bunch of different cardinalities and additional properties. So with this, we move forward to finalizing the taxonomy. So in this step, what we do is that we start with the other data set, SLM, the self-admitted one, and then we go into rounds. So in each round, we take about 20 migrations, and exactly two authors individually label like each of the code changes in those migrations, and we try to use the taxonomy to label them, but sometimes we can't because there are like new things coming out. So we as a team then discuss and resolve the new things, and if there is any disagreements, and we update the taxonomy if required. Then like when we stop is like when there is no new update in the taxonomy, and when we have reached to an agreement. So we actually find that after 3 rounds, we could stop labeling each of the code changes by 2 authors. So we then move forward by labeling them as single authors. So based on that, this is the final taxonomy we have. So we have 6 different different cardinalities. So the difference from the draft version is that we find that there are like some cases where there are only addition of code or only removal of the codes, which we denote as 0 to 1 or like 1 to 0 cardinalities. Then we find a bunch of other different types of program elements. For example, function reference and type, these were not in the draft version. And we find a different properties which are applied to the migrations, to the code changes. And like these lines represent the relations. For example, all these 6, the top 6 different program elements may have we have observed to have change in their names, but only decorator and function calls have different argument related properties. That's obvious because other types of program elements don't really have arguments. So okay, so based on the taxonomy and the data set we have, we conduct an empirical study to find what are the common types of code changes in there. So based on that, we find that there most of 40% of the library pairs and 44% of the library pairs has migration has code changes which has non-function program elements, for example, attributes, decorators, and other things. And in the literature, what we find is that most of the existing techniques only consider function replacement. And then we find that 71% of migrations have argument-related changes, and there is a very limited support in the existing techniques for processing the arguments when doing the migrations. So based on this, what we've understand is that there is a need to further research for supporting more migrations. So to summarize, we have discussed the problem, and we have discussed how we have built the taxonomy, and we have also discussed the findings of our empirical study. Thank you very much.
Thank you, Mohayemin. We'll open up the floor to questions. If anyone has anything to ask, please go ahead. Dr. Adams, please go ahead.
Great, thank you. Yeah, great presentation. So I'm wondering, so given your finding that, okay, the argument processing is not really supported by existing techniques, is there enough data available so that new techniques could be actually built to kind of do that correctly? Because you showed some rather complicated changes in the arguments as well. So do you think there's actually data available that techniques could be learned, for instance?
So like the data set we built by Migrations, and it's like data version 2. We have these like code changes like labeled with what like different kinds of changes are there, and there are like other migration data sets for mostly for Java, but that's not the main thing. But the thing is that they don't have those code changes labeled, so they only have the information that in this commit there is a migration from this library to the to the other library. So like to best of my knowledge, like our data set is the only one that is available right now.
So okay, so then would your data set be sufficient for people to learn thing, or do you need to
So
actually expand on, or
yeah, so let's go back into the like size of our data set. I would not say this is a like big data set. So we have like 337 migrations and only like 1,889 code changes. So this covers like whole different kinds of migrations. So but this is probably still a small number. So like having a like bigger data set would help. But this is a like good starting point, I think. And just to add to that, like we initially labeled just first like 75 migrations. Then after like labeling like about 60 more migrations, we came to a saturation. We could not find any like different types of code changes that is not that we were not like able to like label with our taxonomy. So in that sense, it might be sufficient to say that it covers many different types of migrations.
Cool. Okay, thank you.
Thank you, Dr. Adams. Do we have any more questions? I saw Ahmad. Did you still have a question? Oh, Diego, please go ahead.
Thank you, Mohayemin, for a very nice presentation. I mean, this is a big, difficult problem, right? To sort of assist migration in Python, mostly because, and I hope you all can hear me well, but it's mostly because not everything is in the code. Like a lot of information comes from dynamically information that it runs with Python code. So after doing this, you're probably the biggest expert in the table today on this kind of problem. What would you say is the biggest challenge moving ahead, like to use this data set? And would you be able to even tell like what are the types of migrations that could rely a lot on automated techniques, the types that we still have a long way to go?
So I wasn't like able to hear you very clearly. So I'm trying to see if I understood you. So you are saying that like what would be the next steps, like using this data set or like to like develop migration tools? Is that right? Yeah. Okay.
That's it. Yeah.
So yeah. So like let's talk a little bit about the existing techniques. What they do is that most of the techniques are basically based on the migration data that they observe that these APIs are replaced with these APIs, and so based on this statistical analysis, they try to like find the mappings. But these techniques, most of them only find the mappings, like as an example, like mentioned, that bottle should replace flask, but they do not yet say that this additional argument needs to be passed. So there is another study, like another technique, which is actually for Python, which like does this like mapping of the arguments and actually changing the code. And they use program synthesis for this. But the thing is that like they have evaluated only for like one pair of libraries. That's one thing. But the other thing is that even that the process, like the technique is extremely slow and like not really suitable for like large scale applications. So what I'm actually looking at is like using LLMs to support this, and we have done like very small experiments with with the LLM tools, it seems like it may be like useful, especially if we can feed the data we have built to them and see if these tools can do the migrations. But we haven't started building anything yet, so hopefully we'll be able to answer more a year later.
Wonderful. And maybe just a very quick follow-up. Does your data set has like metadata from the libraries that are moving in their versions that are being installed? Because I hope you can hear better now because I turned off the headset. Is it good?
Yeah, it's better. Yeah.
Right. So does it contain information about the versions of the libraries? Because maybe if you move to a more recent version of Flask, you don't need to pass the argument, or they need to pass a different argument of the other.
Yeah, I understand what you're saying. So in the data set, we don't have this, but I think this is a very good idea you have given. That should be helpful. That should be different. The things should be different from one version to another. Yeah.
Thank you.
Thank you, Diego. Does anyone else have a question for Mohayemin? We do have a few minutes left here. Don't be shy, even some of our new CREATE students. If you'd even like to comment, or if you don't have a specific question, but just a comment in general about what you've heard today from either Divya or Mohayemin, please feel free to chime in.
Laurie, I feel like I probably say this all the time, but really great presentations today, both from Mohayemin and Divya. I don't know, what can I say? You're all superstars. But very, very nice presentations, solid technical contributions, very good presentation, well done on the slides, excellent job answering the questions. So it really sets an excellent standard for all of us. So thank you, Divya and Mohayemin.
Thank you.
Yes, thank you very much. And just for the information and the benefit of our new trainees, each one of you is going to be required at some point during your time in the program to deliver a similar trainee talk just like this. So hopefully today's webinar will maybe get the wheels in motion and get each of you thinking about the topic that you might want to prepare for your own individual webinars. But no rush. Just start thinking about what you might want to talk about. All right, so with that, if nobody else has anything to add, I think we can wrap it up for today. Thank you very much, everybody, for joining, and we'll see you next time.
Thanks, Laurie. Thanks, everyone.
Thank you so much.
Thank you.
Thank you. Bye-bye.
Thank you, everyone.
Bye.
Thank you.
Thank you. Bye-bye.